Section 11.2 leaves off where section 11.1 ended. Remember in 11.1 we were talking about kinetic and potential energy and how they are linked together. If I lose potential, I'm most likely gaining kinetic. Well, this whole idea is called the conservation of energy. Remember, energy cannot be created nor destroyed. It only can be changed. This is just like every other conservation law we've talked about in physics or in chemistry. Like just, for example, the conservation of mass. Mass cannot be created nor destroyed in a chemical reaction. It only can be changed. The same thing with energy. In a closed, isolated system, energy can neither be created nor destroyed, only changed. Think about it. Friction. When friction occurs, you're losing energy, but where's that friction? Where does that get transferred to? Just rub your hands together real quick. What happens? Your hands become warm. That friction, that energy lost of friction is converted into heat. So there's just an example of how energy can be converted. In a section 11.1, we talked about the roller coaster. Potentials converted to kinetic. So when we talk about this, the sum of kinetic and potential in a system is mechanical energy. And that will look like this. The total energy in our system is equal to kinetic plus potential. Or we can say the kinetic initial plus the potential initial is equal to the kinetic final and the potential final. And instead of using initial and final, I used before and after, but it's very similar, same thing. Before is initial, after is final. So this is the key equation here when we start talking about the conservation of energy. KE before plus PE before equals KE after plus PE after. Examples, Winter Olympics are coming up next month. Winter Olympics have tons of sports in which you convert kinetic into potential or vice versa. Think about it. Skiing all by itself is a conversion of energy. You start at the top of the mountain, you slide all the way down. You typically get faster the further you go down the mountain. That's because more potential is getting converted into kinetic. Think of a ski jumper. You are using the potential energy at the top of the hill to jump off and go really, really far distances. All right, bobsledding, luging, all those are examples of converting potential energy into kinetic energy. Sometimes, though, we can lose mechanical energy in the process. Where does it end up going? Well, we talked about earlier, if you rub your hands together, we have friction. You are going to lose it. You're going to lose heat. That heat is a conversion of lost energy. All right. Air resistance. All right. Thermal energy. These are all places in which you can lose mechanical energy. And why machines, as we talked about in Chapter 10, are not 100% efficient, because you can't overcome some of these things. You can't overcome air resistance. You can't overcome friction. So sometimes you lose it. Where does it go? You usually lose it in friction or thermal energy. So you convert kinetic KEI plus PEI is equal to KEF plus PEF. Where's this going to get used? Well, let's look at this in an example here. During a hurricane, a large tree limb with a mass of 22 kilograms located 13.3 meters above the ground falls on a roof 6.0 meters above the ground. Ignoring air resistance, which we have to do, find the kinetic energy of the limb when it reaches the roof. Well, let's use a conservation of energy equation. We have KEI plus PEI is equal to KEF plus PEF. KEI, that's the kinetic initial energy. Is the tree branch moving before it falls? No. So therefore, our kinetic energy is 0. Plus PE initial. Do we have potential energy? You bet we do. So we're going to leave that in there. Is equal to, once the limb falls, and it's right a split second before it hits the roof, it has converted all of its kinetic into potential. It's converted all its potential into kinetic, and a split second right before it lands on the roof, do we have any potential energy? No. So what we're left with here is our initial potential energy is equal to our final kinetic. Well, we want to solve for the kinetic energy? Well, we don't know the velocity of the tree, but we know that PEI is equal to KEF because the other two were equal to 0. So if we solve for PE, that's also KE. So when we solve for PE, PE is equal to mgh. That's equal to 22 kilograms times the gravity, 9.8, times the height between the tree and the roof. Well, 13.3 minus 6.0 is 7.3. When we do that, we end up solving for the tree with 2 sig figs, 1,600 joules. That's the kinetic energy. Now, I could ask you, what velocity did this tree branch fall at? Well, since KE and P are equal, KE would also equal 1,600, and therefore you could set 1,600 equal to 1/2 mv squared and solve for v. That would be an example of how you would do that. So, very simple use of the conversion of the conservation of energy. KEI plus PEI equals KEF plus PEF. Now, when we talk about kinetic energy and potential energy, what we a lot of times start working about is talking about collisions. We talked a little bit about collisions in Chapter 9, and some of the equations are going to be the same. But really, there are two types of collisions. We have elastic and inelastic. And in an elastic collision, potential energy is completely converted back to kinetic after a collision. All that kinetic energy is conserved, and momentum is also conserved in an isolated system. Likewise, we have inelastic, and some kinetic energy is turned into other forms of energy, heat, and what else? No. Anything else that we just talked about, air resistance, any types of energy that we talked about. Kinetic could be converted into stored, chemical, nuclear, whatever it wanted to be. So, when we talk about inelastic and elastic collisions, it's important to point out that many collisions are neither elastic or completely inelastic or elastic. Usually it's a little bit of both. So that is when we talk about collisions. When we talk about collisions, we can have the granddaddy of all problems. This is a very timely problem since it talks about an accident happening on slippery roads. In an accident, this question's probably, this is like 8 years old when I used to drive a Corolla and Mr. Selk had a Tahoe. Neither of us have those vehicles anymore, but we'll work with it. In an accident due to slippery roads, my Corolla, which has a mass of 595 kilograms, is moving at 15 meters per second, smashes head-on into Mr. Selk's Tahoe, which has a mass of 1,575 kilograms, originally moving in the same direction at 5 meters per second. The cars lock together, acting as one, and move forward. What is the final velocity of the wrecked cars? Remember from earlier in Chapter 9, MAVA plus MBVB is equal to MABVAB. Because the cars are mushed together, we're going to have one final mass and one final velocity. Get that equal sign figured out. So the Corolla is A and the Tahoe will be B. So when we plug in numbers, we're going to have 595 times 15 plus 1575 times 5 is equal to MAB. Well, you add the masses of both vehicles together. 1575 plus 595 ends up being 2170 times VAB. You do some algebra, you rearrange, and you get with sig figs, VAB equals 5 meters per second is 1 sig fig, 8 meters per second. So like we said, that equation is what we already had. So if we look at part B, how much kinetic energy was lost in the equation? Well, when you're figuring out lost kinetic energy, the change in kinetic energy is really equal to, well, let me erase that. The change in kinetic energy is equal to your final kinetic energy minus your initial kinetic energy. So what we're going to have here, if we set this up, My KE final, 1 half mv squared, minus my KE initial. But my KE initial is I have two separate vehicles, so I'm going to have two separate initial kinetic energies. I go ahead and I'm going to plug everything in. My KE final would be my final wrecked car. So 1 half times the mass of both cars lumped together, which remember is 2170, times v squared, which we just solved for, minus the initial kinetic energy of the Corolla. So we'll go 1 half times 595 times 15 squared, minus the initial kinetic energy of the Tahoe, which is 1 half times 1575 times 5 squared. When you figure that all out, what you end up getting is our change in kinetic energy was negative 17,000 joules. Go to step C. Step C. What fraction of the original energy was lost? Well, how are we going to figure that out? Well, the change in KE over our initial kinetic energy, which would be KE A initial plus KE B initial. And really, we're just figuring out for the two cars. So when we do this, this is a kind of a new equation, but really it's just figuring out a percent. Change in kinetic energy divided by, you're taking your lost over what was there initially. So when you do that, our change in kinetic energy we figured out was negative 17,000 divided by the kinetic energy of the initial kinetic energy of A, which is 1 half times 595 times 15 squared. That's the Corolla. All right. Plus the kinetic energy of B, which is the initial kinetic energy of the Tahoe, which is 1 half mass, which is going to be 1575 times 5 squared. When you go ahead and you figure this out, you end up getting a decimal, which is 0.196. We sig fig, and we have 20% of our kinetic energy was lost. Now, second to last question. Into what forms did that energy go? Where's that energy going to be converted? Well, it's what we talked about. Friction. And have you ever seen two cars get wrecked together? They're going to mash together, and they're probably going to create a fair amount of heat or thermal energy. So that is where that can go. And lastly, because Mr. Kleinert was not paying attention and going too fast on the slippery roads, will I survive the wrath of Mr. Selk in the accident? And the answer to that is very probably much no. I will not. So this is using the conservation of energy with the equations we have, with using kinetic energy, which we got in 11.1, using potential energy, which we got in 11.1, and going forward from there. So this is kind of tying all our energies together. We have KE, we have PE, and we know they're related.